Okay, so what I'm going to do in this video is I'm going to prove this statement, right? So this statement is called the arithmetic geometric mean inequality, or AMGM for short. So it's abbreviated AMGM for short. So what it states is that for all non-negative real numbers, A1 through AN, the arithmetic mean, right? So the sum of the AIs divided by the number of the AIs, which is n. This is going to be greater than or equal to the product of all these AIs taken to the power 1 over n, the nth root. So this part is the arithmetic mean, and this part is the geometric mean. And so what we're going to do is we're going to prove this by induction. And so regular induction doesn't work here. Well, not in the usual sense. The standard proof is something much more clever, and I think it's due to Cauchy, and it's called, well, the informal name is called leap forward, fall back, and you'll see why. So okay, and then let's add that n is greater than or equal to 1. So let's try the small cases, right? So when n equals 1, what does this inequality become, right? Well, what happens is we have this 1 over 1, and then a sum from I equals 1 to 1 of a sub I, which is just a sub 1, right? And then we have, you know, the product from I equals 1 to 1 of a sub I to the 1 over 1, which is just a sub 1. So there's nothing to prove here. So this doesn't really give us any information about how we might try to solve this much more general inequality, right? So let's go up another number, right? Let's go to n equals 2. So now we have x and y are non-negative integers. I meant non-negative real values. So we want to show that, well, x plus y over 2, right? That's the arithmetic mean in this scenario. And then we want it to be greater than the geometric mean. So just the square root of x times y. So the square root of x times y. Okay, so I guess, so let's try to work with this inequality, and maybe we'll see that this will become something that is easier to work with. So let's do that. So with x plus y over 2 greater than or equal to xy, right, we might try to square both sides. So this is if and only if x plus y over 2 squared is greater than or equal to xy, right? Because implicitly, like, this is greater than or equal to 0, right? So, and since these two things are both non-negative, right, it turns out showing this is true is just equivalent to showing that this is true, right? So what we're going to do is we're going to multiply both sides by 4, right? Because this is, you divide by 2 and square it, right? So once you expand it, you'll get a fraction that has 4 in the denominator. So we'll multiply by 4, right? which is a reversible operation. And we'll get x plus y squared is greater than or equal to 4xy. And this, right, we might expand the left-hand side and get x squared plus 2xy plus y squared is greater than or equal to 4xy. Okay, and then we subtract 4xy. So we get x squared minus 2xy plus y squared is greater than or equal to 0, which is just the same thing as x minus y squared is greater than or equal to 0, which is always true. So since the whole series of steps was completely reversible, it follows that the original thing we wanted to show is true, right? And I guess if you're not comfortable with starting from the conclusion and then coming across something completely true, you can start with this observation first. You may start with this observation first, and then you can go backwards and then get to the conclusion that you want, which is the case when n equals 2, right? So now we have n equals 2, right? So we can take two values, and then their average is going to be greater than the square root of their product. Okay. So here's what we're going to do, right? So with a little more work, right, we can get the n equals 4 case. In fact, from the n equals 2 case. So let's do the n equals 4 case. Right, so this is a1 plus a2 plus a3 plus a4 over 4 is greater than or equal to the fourth root of a1, a2, a3, a4. So what do we do? Well, here's what we can do. So what we're going to do is we're going to use this specific case, right? So what this side is, right, a1 plus a2 plus a3 plus a4 over 4. Well, so a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 over 4. Well, this is equal to 1 over 2 times a1 plus a2 plus a3 plus a4 over 2, right? And so now we can use the n equals 2 inequality that we just proved, right? So this is going to be greater than or equal to 1/2 of the square root of a1 plus a2 times a3 plus a4. Okay, so now we have this, right? And so this isn't quite what we want, right? We want a product of all of them. And now we have product of sums of both of them, right? Which isn't quite what we want, but that's okay actually, right? If we bring the 1/2 into here, right, this becomes, this whole thing becomes a1 plus a2 over 2 times a3 plus a4 over 2. What I did is I brought the 1/2 in, right, into the square root. It becomes 1 over 2 squared, right? And so there are two 2's here. But now, right, we can use the inequality yet again. So we get that this thing is going to be greater than or equal to the square root of the square root of a1, a2 times the square root of a3, a4, right? So it's the square root of square roots. And then we can do some combining of the square roots, right? In the standard way. And then this is exactly what we want. So that's the n equals 4 case, right? And so you'll notice that I proved it using two applications of this n equals 2 inequality, right? And so when n is very general, this argument will work for proving very specific inductive steps. So let's do a certain inductive step. So let's assume that the sum from I equals 1 to k of 1 over k a sub I is greater than or equal to the kth root of the product I equals 1 to k of the product of the terms, and then take the kth root. All right. So now let's see what we can conclude about 1 over 2k times I equals 1 to 2k, right? So we're assuming that this case is true, right? The AMGM inequality is true in the case when n equals k. Now let's see what happens for 2k. Okay, so we have this sum, right? We can divide it into 2, right? So the sum goes from I equals 1 to k, and then you can go from I plus 1 to 2k, right? And they'll have the same number of terms. So this sum right here will split into 1 over 2k times the sum from I equals 1 to k of a sub I. And then we're going to add the remaining terms, right? So this is I equals k plus 1 to 2k of a sub I. Now you'll notice that both sums, they have k terms in them, right? So they're exactly of the hypothesis of this, right? Except for the 1/2, but that's okay, right? So we're going to apply the inductive hypothesis, right? So this is greater than or equal to 1 over 2 times the kth root, the product from I equals 1 to k of a sub I, well, 1 over k, and then plus half of this product, right? The product from I equals k plus 1 to 2k of a sub I to the kth root. Okay, so now we have, well, so now let's observe that we can take the 1/2 out, right? And notice that this is really an average of this term and this term, right? So this is equal to this product I equals 1 to k of a sub I, 1 over k, plus the product from the indexes k plus 1 to 2k of a sub I, all over 2, right? And now we can apply our n equals 2 case. So we know that this is greater than or equal to the square root of this thing times this thing. So let me write that out. It's the product from I equals 1 to k of a sub I, 1 over k, and then times the product from k plus 1 to 2k of a sub I, 1 over k. And then we can do some combining, right? So we can turn this square root into an exponent 1 over 2. So this is, so we're going to combine these two things, right? Because they share the same exponent. So we have the product from I equals 1 to 2k of a sub I. And that's to the kth power. And we also have the square root, right? So we have to take things to the half power. But this is I equals 1 to 2k of a sub I to the 1 over 2k, which is exactly what we wanted. Which is exactly what we wanted. We showed that this is greater than or equal to this thing. Okay, so now here's what we know. We know the 2k's, we know that n equals 2k's, right? And we know that if we have this inequality, right, for the value k, we can prove the inequality for the value 2k, right? So in, I guess, if p of n is the statement that the AM-GM inequality is true, it holds for n, then we've shown that p of k implies p of 2k. And we've also shown that p of 1 and p of 2 are true. All right, so we have 1, 2, and then we have this doubling property where we can double over and over again. So what do we need? We actually, what we need to do, what we need, right, is a way to go backwards, right? Because with just these things, with just these rules, we only have that this inequality is true for all powers of 2, right? We don't even know that the inequality holds yet for n equals 3, right? Which is the next case after 2. These rules aren't strong enough to prove anything for all n. So what we need to do is we need a way to go backwards, actually. So if we had a way from p of k being true to show the previous case is true, then we'd be pretty good. Here's the idea. It's very clever. So we're going to assume, again, so we want to show. I'm going to show this, right? So, okay, so we're going to assume again that the average of the AIs is greater than or equal to the geometric mean of the AIs. So now we want to show that this inequality is true for any positive values of AI, that the k-1 average, k-1 of like some bi is greater than or equal to the product of those bi, right? And you take the k-1 through, right? So we have to somehow use this inequality to prove the previous inequality, right? And so you can immediately see some difficulties with doing this, right? So the first thing is that in the sums, right, one of them is a sum of k terms. Another thing is a sum of k-1 terms. So it's not really clear how we're going to turn k terms into k-1 terms. right? The next thing we have to note is that we have a kth root here and a k minus 1th root here, right? So it's not really clear how we'll get this product to turn into this product. And so the really clever idea, right, is we have to translate both these ideas to prove this inequality, right? So we know this thing is true, right? And so here's what we're going to do, right? So we're going to take, so we want to show an inequality of this type is true, right? So we want to start with something like this, right? And in fact, we want to translate this into something like this, right? So how are we going to do that? Here's what we're going to do, right? And this is the very, very clever idea. We are going to pad, we're going to take a sum like this, and we're going to pad it, right? We're going to add one more term so that the average doesn't change, right? So we're going to take our, so we're going to consider our average, 1 over k minus 1 times I equals 1, k minus 1 of the bi, right? And, you know, of course, by the hypotheses of the problem, the bi are all greater than or equal to 0, right? So we're going to consider our average this, right? And so, and we're going to call it, let's call it C. C, capital letter C. All right. So let's see what happens, right, when we take 1 over k times the sum from I equals 1 to k minus 1 of the bi plus C, right? So essentially what we're doing is we're taking an average of the bi and then, you know, and then this C, right, the average of the bi. And it turns out actually it's going to be the same as, it's going to be C, right? So here's the argument, right? So we're going to have to expand. And this is going to be 1 over k times I equals 1 to k minus 1 of the bi plus 1 over k minus 1 times the sum of the k minus 1 terms again of the bi. So this is going to be, if we write in front of this, right, k minus 1 over k minus 1, right, and use the distributive properties, then this is going to be 1 over k times k over k minus 1, and then the sum of the bi's. And then so then you can see that this is obviously C, right? So actually, right, we can take this sum, right, which is in the left-hand side of what we want to prove, right? And we can consider it as an average of an arithmetic mean of k values, right? And this is inevitably how we're going to use the inductive hypothesis here. Okay, right. So with the terminology that I've just introduced, right, what we have, the sum from I equals 1 to k plus 1. Oops. I equals 1 to k minus 1, right, the average of the bi's is equal to this average, right, the k average, I equals 1 to k minus 1 of C, right, plus C, where C is, as we introduced earlier, right? All right, and then we're going to use our inductive hypothesis. And it's going to be the product of the bi's, and then also times C at the same time, right? And taken to the 1 over kth power. Okay. And now we're almost done, right? So let's write this inequality out, right? And we're going to get what we want. So let's see. Oops. All right, so we have 1 over k minus 1 times the sum of the bi's is greater than or equal to c, right, which is the sum over here, which is the sum of, well, it's actually just the same thing, right? k1 to k minus 1. And this should be an I, right? And it's a b sub I. And then 1 over k times the product from I equals 1 to k minus 1 of b sub I, which is 1 over k, right? And so we need to figure out how to turn this into a k minus 1. But this will all work out in the end, right? Because this term and this term, right, are the same, right? So this is really k over k. So we can divide out. We can divide out. And so we're going to divide out by this thing. We're going to divide out by the average of the b's times the power of 1 over k. So we're going to divide out by this. Okay. And here's what we're going to get. We're going to get 1 over k minus 1 times the sum of the bi's. K minus 1. Aha, here's where k minus 1 appears in the exponent, finally. It's going to be greater than or equal to, since this thing got divided out, we have the sum from I equals 1 to k minus 1 of the bi's, and then to the 1 over kth power. So, okay, so now we're going to take things to the k over k plus 1th power, right? So we're going to take things to the k over k minus 1th power, which is okay because all the power maps are increasing functions. So we're going to take things to that power, and that is going to imply our conclusion. So let me repeat what I did here, right? So I had an inequality and I took both sides to the k over k minus 1th power, which is a positive power, right? So I'm assuming k is greater than equal to 2 here, which is a positive power, right? And these two things are both greater than or equal to 0. So taking both things to a positive power will preserve the inequality, right? So that's how I can finally get this, right, as desired. So that's what we did, right? So we finished the problem. So what we've shown, right? So if we let P of n be our AMGM inequality, right? We showed that the cases n equals 1 and n equals 2 are both true, right? 1 was very easy, 2 is a little bit more involved. And then we showed that if we have a k case, we can prove the 2k case. But that's not enough to just show this holds for all n, right? Now we also need to show that we can go backwards, since for this you can go to infinity in a loose sense, right? And then you can go backwards, which means you can cover everything. So that is the leap forward fallback induction. So hopefully that was instructive.